So we have completed electrostatics and the next chapter is magnetic field. So before starting we need to get some basic idea about magnetic field. So today we will study about introduction to magnetic field. So the first question is, what is magnetic field? A magnetic field, it is the region around a magnet or a current carrying conductor up to which its magnetic force can be felt. A magnetic field is the region around a magnet or a current carrying conductor up to which its magnetic force can be felt. It is similar to the electric field. What is electric field? Electric field is the region around a charge up to which its force can be felt. Similarly, magnetic field is the region around a magnet or a current carrying conductor up to which its magnetic force can be felt. Magnetic field is a vector quantity. It has both direction and magnitude. The common unit of magnetic field is Tesla or Newton per ampere meter. We have another commonly used unit of magnetic field is Gauss. Another commonly used unit of magnetic field is Gauss, and 1 Tesla is 10 to the power 4 Gauss. Next point, the magnetic effect of electric current was discovered by Easted, and the detailed study was done by Biot and Savard. So the magnetic effect of electric current was discovered by Easted, and the detailed study was done by Biot and Savard. And we will study about Biot-Savart law in the next class. The direction of magnetic field is represented by magnetic field lines. Similarly, we have studied that in electric field, the direction of electric field is represented by electric field line. Similarly, the direction of magnetic field is represented by magnetic field lines. Next point is magnetic flux. It is the total number of magnetic field lines passing normal to the given area. Magnetic flux is the total number of magnetic field lines passing normal to the given area, and phi is B dot A. Since phi is the dot product of B and A, phi is a scalar quantity. It has only direction. Phi has no magnitude. Sorry, phi has only magnitude. Phi has no direction. Phi has only direction. Phi is scalar, no direction, only magnitude. Phi is a scalar quantity, it has only magnitude, no direction. Phi equal to B A cos theta. Phi equal to B dot A. Phi is equal to B A cos theta, where B is the magnetic field intensity, A is the area, theta is the angle between B and A. The unit of magnetic flux is Tesla meter square or Weber. So we have the unit of B as Tesla and we have the unit of area as meter square. The unit of magnetic flux is Tesla meter square, or it is commonly known as Weber. Idea of magnetic field. Suppose we have a current carrying wire and we place a charge plus Q at rest at the point P. The charge experiences no force. The charge will stay at the point P at rest. Suppose we have a current carrying wire with a current I and we have a point charge, it's a positive charge plus Q at rest. So in this case, the charge Q experiences no force, it will stay at rest. We have a current carrying conductor I and we have a point charge Q which is at rest. So in this case the charge will experiences no force. There is no force of attraction or repulsion. This means that there is no electric field or force to attract or repel the charge. But if the charge is projected in the direction of current, the charge will deflect towards the wire. Assume that the charge is positive. We have a positive charge here, and if we projected in the direction of current, the charge will deflect towards the wire. When the charge was at rest, there is no force of attraction or repulsion, but when the charge is projected in the direction of current, it will deflect towards the wire. This indicates that there must be a field at P that can exert force on moving charges but not on resting charges. This field is different from electric field that always exert force on charges irrespective of whether the charge is at rest or not. Initially, when the charge was at rest, there was no force of attraction or repulsion, but when the charge is projected in the direction of current, it is deflected towards the wire. This indicates that there must be a field at P that can exert a force on moving charges but not on resting charges. This field is different from electric field. An electric field can exert force irrespective of the fact that whether the charge is at rest or moving. An electric field can exert force on a resting charge as well as a moving charge. Here, there was no force of attraction or repulsion when the charge was at rest. The force of attraction or repulsion comes only when the charge is projected. So we can say that this force or the field here is different from electric field, and this new field is called magnetic field. This new field is called magnetic field B, and the force is called magnetic force. So the next point is there is one line such that if the velocity of particle is along that line, there will be no magnetic force, and we define the direction of this line as the direction of magnetic field. That is, there is one line such that if the particle is moving in that line, there won't be any magnetic force, and we define that direction of line and we define that direction of line as the direction of magnetic field. Got it? There is one line such that if the velocity of particle is along that line, there will be no magnetic force, and we define the direction of this line as the direction of magnetic field.